Okay, welcome everybody to this week's Colloquium. Today it's my pleasure to introduce the speaker, our guest, Professor Ian Galbraith from Heriot-Watt University in Scotland. Ian, as I know him, is actually a semiconductor physicist, and I know him for many contributions he has made over the years in semiconductor optics. But today he will actually not talk about semiconductor optics, at least not inorganic semiconductor optics, I should say.
Yep.
Ian got his PhD in 1986 from Heriot-Watt University and moved on to be a postdoc in Germany in Hartmut Haug's group, I believe. Later on, he was with Philips Research Lab in the UK. And around that time, he actually was a postdoc briefly here in Tucson. He was actually a postdoc together with me. We were together postdocs here, and it so happens that our former boss is even in the audience, Professor Koch from Marburg now. So I've known Ian for a long time, and I asked him what year was it that he was here, and he said, well, it was the year when the wall came down. And I bet you most of the students here don't even know what wall came down. At any rate, Ian then later became a faculty member at Heriot-Watt, first as a reader, and then as a professor, and then he spent a lot of time doing administration. He was the department head at the Department of Physics, and for 3 years, I think, and he was the director of research for the School of Engineering and Physical Sciences, which encompasses chemistry, mechanical, electrical, and chemical engineering, as well as physics. So that was a heavy administrative job, I bet. Anyways, we look forward to today's talk, which will be on optical physics in organic semiconductor molecules. Thank you.
Okay, thank you very much. Thanks for the invitation and the opportunity to speak. It's nice to meet up with some, I was going to say old faces, but that's not very politic. Some faces I've known for a long time. Actually, there's somebody at the back there who I've known for even longer than I've known Rolf and Stefan, as Ewan Wright and I were office mates all those years ago when we were both doing our PhDs. I do have stories that I can tell later in exchange for dollar bills, but I'll keep them to myself for now. So I'm going to talk today a little bit about some of the work that we've been doing in looking at the optical physics of a different kind of semiconductors to the ones that I've usually been working on, inorganic semiconductors. So I'm going to talk a bit about organic semiconductors. So an overview of my talk will look something like this. I'm going to try and motivate the work a little bit by saying why are organic semiconductors an interesting thing to spend your time looking at. Talk a little bit about, for those of you who are not in that game, what these materials are, what they look like, and a little bit about their optical response. Then I'll get into more of the meat of the talk, talking about the ultrafast and not only their pulse propagation in these materials, and something about the excited state processes and dynamics that are important to the optical properties of these materials. And then I'll wind up. So why organic semiconductors? Well, in contrast, and maybe compared to inorganic materials like silicon or gallium arsenide, these are flexible, cheap, printable, easy to process materials that are very promising for plastic electronics and optoelectronics. And there's a wide range of applications that these have already made it into the market, and there are other more equally promising applications where they're still emerging. So some of the advantage are things like roll-to-roll processing. So in other words, where you just have a big roll of material and you process it in a continuous way. And this may be very important, for example, in making large area solar cells. Another important aspect of these organic semiconductors is they're biocompatible. And what by that I mean that if you eat them, you don't poison yourself. So if you want to make some kind of measurement of the inside of your stomach, and the doctor wants to give you something to swallow, then it's a good idea if that helps you get better and not the other way around. So organic semiconductors are very compatible with people in that sense. And also maybe, for me, the equally interesting part of it is that there's some interesting science that you can do to try and answer or understand the properties of these kind of organic materials. So I take one application that's already out there in the market that of organic semiconductors, and this is it just happens to be a Scottish company because I know about it, but this is a device for doing photodynamic therapy. And photodynamic therapy is something that gets used to treat benign or skin cancers. And so basically they rub some magic stuff that the pharmacists develop onto your skin, and then that stuff gets absorbed into the skin. And then in order to photoactivate it, you have to illuminate that patch of skin where the melanoma is for a length of time. And this length of time can be quite long, so it's some number of hours. And that's inconvenient, if you like, for the patient if they have to do this every week or every day or on a very regular basis. So what this Ambicare company have developed is an organic semiconductor-based kind of light plaster. So it's essentially an organic semiconductor that you can attach to yourself in this way, just no more inconvenient than wearing an iPod, and then you can sit and do the important things that we all do nowadays, which is use our Macs to surf the web while you're taking this treatment. And so this is a very important development just in terms of making healthcare accessible and convenient for people. Perhaps more technical applications are that people are people are making photonic devices out of these materials. So things like waveguide amplifiers. So this is a silicon and silicon oxide substrate, and then with the active material in this waveguide structure embedded in some photoresist, and then you have a waveguide structure along here where the light propagates. And you can make optical amplifiers out of these types of waveguide structures. You can do in-plane coupling, so you can couple a signal beam in through some waveguide coupling, pump the active region of the waveguide, and couple the amplified signal out again through Bragg gratings. And in a similar geometry, you can look at doing all optical switching, where you pump this structure, and a third beam then controls the inversion in this structure and either switches in or out optical pulses. So these are the kind of photonic devices that are being developed, and the kinds of processes that we're trying to understand that control the performance, perhaps, of these kind of devices. You can also make laser optically pumped organic semiconductor lasers, and that's another active field. And although I haven't worked myself too much in that area, much of the physics is the same, but we haven't really looked too much at lasing. So what kind of materials are we talking about here? Well, these are conjugated polymers, and the base unit, if you like, of these conjugated polymers is often something that's called a fluorine unit. And a fluorine unit, if I can point at this one instead of that one, is this kind of motif here, where you have two rings of 6 carbon atoms, just like in benzene, with an extra one forming the top of this pentangle. So you have 13 carbon atoms, and that's the same as this. And all these bonds coming out the way, these are all either just simple hydrogen bonds on the outside, or there are some longer structures, as you can see here. And these longer structures don't really play a big role in the photophysics of these molecules, but they're important for their properties like solubility or the morphology of a film that you lay down. Then these big side chains have an important influence. So the real photophysics goes on along these fluorine-based units that form the backbone of the polymer. And sometimes they're not just a simple chain like this. They sometimes have other units in them that have particular functionalities that localize the excitation on the particular parts of the backbone. I should say, because I found it very confusing in the beginning, this is called polyfluorine, so this kind of structure here, but it has no fluorine in it. It has none of the atoms fluorine in it. Okay, and it's called fluorine because it's very bright. Okay, so it fluoresces very strongly, so the chemists call it fluorine. But for a simple physicist, that was confusing in the beginning. The types of properties that, if you like, describe these kind of materials are that there are a few electronic transitions around the fundamental absorption edge that are important. So you can hope to handle that number of crucial transitions. There are very strong excitonic effects in these materials, which have a binding energy of about half an eV. So the excitons are very small. They're localized around just a small number of these units. Typically, the excitations that you see are the excitations of the chains themselves and not of some aggregation of the chains. So it's not like you take all these molecules and they form some kind of super molecule when you put them down together. You tend to be able to understand what's going on by thinking of the properties of the independent molecules and their interactions. And the other thing that makes it very different from inorganic semiconductors are that the atomic conformation, the arrangement of all the atoms, depends on the excitations in the molecule. Okay, so if you have a particular conformation or arrangement of all these atoms in the ground state, and then you absorb a photon and excite some excitation up to a higher lying state, then all these atoms move a little bit. Okay, and that changes all the electronic states, changes all the dipole matrix elements and stuff. So this is rather different to the case that we're used to in gallium arsenide, for example, where we have a band structure in the material. We have an E versus K, and that band structure is kind of fixed. It's a kind of ladder of states that we run up and down and we do all our interesting physics on. But that backdrop is always the same. That's not true in this type of material. So I kind of came to this from talking to the people who were doing experiments in these organic materials and bringing to it the understanding of how gallium arsenide-based devices worked, and saying, well, how do these organic devices work? I don't really know what the physics is going on in there. So we decided to try to do some modeling of these organic materials to understand the microscopic processes going on in these materials. So in principle, you start with something that's a big mess, and is a big complicated arrangement of all these molecules. But these molecules or these polymers, they all have, you'll see they have kinks in them, and the optical properties tend to be dominated by what goes on between the kinks. The kinks kind of cause a break in the conjugation, and so if you like, the bits between the bits, each kink defines a region or a separate, almost like a separate molecule. So we can map this kind of material onto some a set of interacting chromophores between the kinks, but this is complicated by you have strong coupling to the phonons or to the vibrations within these molecules. So you have to worry about that. You have Coulomb coupling between the chromophores, because if you make dipole excitations, you excite a dipole on the chromophore. And in these types of devices, like an optical amplifier, you want to be dealing with intense light fields, and so you want to make something that's non-perturbative in the light field. Okay. So the approach that we've taken is to look at single chromophore properties to try and understand how we can even model that part of it, and then to look at solid-state systems made up of these single chromophores, where we investigate the migration of excitations and the annihilation of excitations, and I'll come back to that in a minute. So there hasn't been a huge amount of work done on trying to understand if you like, starting from the molecular basis of the material through to a device. And so we thought we would try and make some progress on that. So when we begin to think about the optical processes in these materials, we can hark back to what we think of in what we're taught in class about valence bands and conduction bands in materials like silicon or gallium arsenide, where we excite an electron from the valence band to the conduction band. It maybe relaxes down, And then in a laser or an optical amplifier, you have an emission process that takes the electron back down from here to here. And then you can complicate this process with all the Coulomb interactions between the electrons and holes and everything else. But that's basically a picture that captures the essence of what's going on, and you're looking at the energy of an electron or a hole and the momentum of an electron and hole. Okay? And this momentum is a good quantum number because you have this translational invariance of the lattice. You have this good picture to work in and for the electrons to run up and down in. When you come to organic materials, you lose this translational invariance, so momentum isn't a good quantum number anymore. And that's always bad news for a theorist when you lose a quantum number. That's not a happy time. And the way you have to think of the absorption processes in these organic materials is to think of a manifold of states, and the way they're described is this S0 is the highest occupied molecular orbital configuration. So this is where, before you make any excitations, the electron states are filled up to this level, and there's a series of vibrational levels corresponding to this electronic state. So these are the atoms moving back and forth in the presence of the charge distribution that the electronic states provide. And so there's a series of vibrational levels, and you make excitations from these vibrational levels, either the ground state or some other ones, up to a higher lying electronic state. So in other words, the electron distribution changes in going from this highest occupied molecular orbital to the lowest unoccupied molecular orbital, which is what this stands for. And so the dipole transitions that you make are going from here to here or here to here. And now you have a different electronic charge distribution, and that means that the atoms themselves see a different space charge, and so they move a little bit. And this is what I was talking about when I said the molecular conformations depends on the electronic charge distribution. So that's why this parabola is not centered at the same point as here. Okay. Now this is some kind of generalized axis here. This is not just one coordinate. It doesn't mean that everything just shifts over a little bit. All the atoms move a little bit, and you could think of this as a...
This has to do with the matrix in which these things are embedded. So the matrix is solid like glass. You won't have this deformation, but if the matrix is flexible, then you will have the deformation.
Well, for example, if you were in solution, then you would have this change. This change comes about because of the electronic distribution, the change in the electron charge from here to here.
But if it was embedded in solid glass?
It depends on how tightly it's embedded, if you like. If it's really frozen and unable to move, then of course they can't move. But that's not what you see in most situations. Even in a film, you still see some shift in the minimum of here compared to here, and that gives you the Stokes shift in the emission. So this is in a way a more complicated picture than we have to deal with in inorganics. So the first thing we did was we wanted to try to see if we could describe that simple picture quantitatively and get some, if you like, some confidence that we knew what we were talking about. So the first thing we did was that we took this kind of fluorine molecule, and we did density functional theory calculations of the electronic states of that molecule. So this is essentially quantum chemistry, and there's two ways you can do quantum chemistry. If it's your job and your career, you can develop your own code. If you just want to use it as a tool, there are commercial packages that are able to give you reliable results for given molecules. And so we used a code called Gaussian to do the density functional theory. And this gave us a set of electronic transitions, a set of vibrations for this kind of molecule, and dipole matrix elements. And so from this, we were able to calculate what just the linear absorption of this molecule should look like, or the linear emission. Okay? And so what you see here is a calculation based on eight units of this fluorine, so 8 of these kind of little units end to end. And this is an experiment that is measured on a polymer system. And what you see is pretty good agreement between the two. So that gave us some confidence that we were able to understand and quantitatively describe the electronic states in this material. So, to cut a long story short, we did that for a number of different lengths of molecules, and we did experiments where chemists made samples where they controlled the length of those molecular units. One thing I've come to learn in doing this work is an appreciation of how clever some chemists are. They are able to make 2 of these units together, or 3 or 4 or 5, and they're sure that they're 99.99 just 3 of these units. So we made measurements and calculations for a differing number of these fluorine units, and the details are not hugely important, but this is a mixture of theory and experiment points, and you can see they all pretty much agree nicely with each other. The energy band gaps are somewhat less good than the dipole matrix elements, but again follow the trend is very close. So we're pretty confident that we can get good information on these types of fluorine oligomers. One interesting thing that came out was that, of course, with these kind of alternating units, there's different units. You could either have all the units so that they were just lined up, all flat in a plane, okay? But actually that's not the minimum energy configuration. The minimum energy configuration is something that has a slight tilt between the 2 units, okay? And that's not even all you have, in the sense that you could either have a kind of helical structure where these units all twisted round each time like a spiral, or you could have it that they alternated back and forth. And what you find when you do the calculations is that this kind of helical structure stays in a straight line. Okay, so the big long chain stays straight. If you have this alternating configuration, then what you find is the molecule tends to bow, okay, in the minimum energy configuration. And the energy difference between these two is not really all that big. So in a kind of thermal sample, you've probably got some mixture of these two going on. Okay. The other thing that happens is that you get self-trapping of the excitations once you've absorbed a photon. So what's plotted up here is the electronic transition density in this S0 geometry. So what do I mean by that? I mean, this is the change in electronic density that occurs when you absorb a photon in this ground state geometry. So in one case you get an increased electron distribution, and in another place you get a decreased electronic distribution. And you can see that the excitation is more or less along the whole chain. So it's quite a delocalized excitation that you get across more or less the whole chain, apart from something at the ends. Then what happens is that, as we talked about, the atoms then start to relax in response to this change in electronic distribution. Okay, so they all move, and what happens then is that this excitation gets trapped in the middle. So you find that the atoms here have moved around and localized the excitation in the middle. So it's a bit like throwing a bowling ball in a trampoline. So you kind of it all kind of gets stuck in the bottom. And what the other and the way that they rearrange themselves are actually to make themselves more planar. Okay, so remember we started off with, say, that one of these helical distributions. So that's what this looks like underneath all these curves. But what the rearrangement does is cause these fluorine units to line up in a plane. So it flattens them off as one of the effects of this excitation self-trapping. Okay, it also changes then dipole matrix elements and everything else, and band gaps. So we had got to the point where we felt confident we could understand what was going on in a single one of these oligomers, and how that related maybe to a polymer chain. But real devices aren't really made of singular oligomers. They're, and nor do they just use linear optics. So we better try and do something about that. So we need to think about the way that these organic molecules respond to strong optical fields and how they interact with their neighbors, and how do excitations move or get distributed into these in these systems. So we're going to look at the first of these first, and we're going to look at a density matrix approach based on these electronic states that we get from the quantum chemistry. So a theorist always starts with a Hamiltonian, and so what we have here is a Hamiltonian for the molecule, where we have the energies of these electronic states. We have the coupling to the vibrations. So the vibrations are these creation destruction operators for vibrational quanta, with an energy that is the energy of that vibrational quanta. The creation and destruction operators for the electronic states are these C's. And then we have a coupling to the dipole or to the optical field through a dipole interaction, which is mediated by a dipole matrix element that we also get from the quantum chemistry. Okay, so we get the energies. We get the energies of the electronic transitions, the energies of the vibrations, and the couplings, the dipole couplings to the optical field, all from the quantum chemistry calculations. We then put this Hamiltonian into an equation of motion for the density matrix, and we can arrive at a set of a set of differential equations for this density matrix. And the elements of the density matrix are that the diagonal ones give you the populations of all these states, so how many excitations do you have in those states, and all the off-diagonal ones give you coherences, give you polarizations between the various combinations of states. Okay, so these off-diagonal elements describe to what extent are the different states mixed up. There's also a coupling to a heat sink that is not treated in any terribly fancy way. It's just a dissipative term. But the way that these density matrices couple back to the optical field, to this E, are through these off-diagonal density matrix terms. So these polarizations, and I should emphasize again, what I mean by polarization is dipole moment per unit volume. I don't mean polarization as in linearly polarized or circularly polarized or something like that. So these internal dipoles that are generated by the electric field then act as a source, a polarization source in Maxwell's equations, which then give rise or couple back to the electric field. Okay, so we can describe the propagation of a pulse, an E of R and T, through this material by going around this loop and looking at, starting with the electric field, and this generates some polarizations and populations that then is propagated through the structure and feeds back into the generation of the light at a later time slice. So we solve numerically these equations via propagation in space and time, just with a transfer matrix approach and using a Runge-Kutta scheme to solve the differential equations. And this is non-perturbative in the light field and includes the propagation of the light.
Am I right that your Hamiltonian doesn't include relaxation by phonon emission? It looks like you've got a scattering capability, but not a relaxation.
That's right. It's kind of buried in here, to be honest. So you're right. It's not in Hamiltonian. So this is maybe just repeating myself here a little bit, but it's worth just remembering what happens when you absorb or when thinking about what happens when you absorb a photon on these ultra-short timescales. You excite an electron down from this vibrational state to a higher one, but at very short times, your atoms, the underlying atoms or nuclei, haven't had a chance to move. Okay, so you have this S1 electronic distribution, but that's not the appropriate electronic distribution to couple to where all the atoms are. So all the atoms, if you like, are out of sync with where the electron distribution is. And so one way to think of it is that you're exciting some linear combination of all these normal modes or vibrational normal modes in this S1 geometry by exciting the electron from down here to up here. And it's only through the dissipation of energy that you were talking about of these vibrational modes out to a heat bath does the system actually come down to the ground state of this S1 geometry. So in other words, you reestablish an equilibrium between the electronic distribution and the position of all the atoms. And that happens in a picosecond or less. So it happens relatively quickly, although measurably so. The complication for us is a little bit that it gives us was one set of phonon modes in this geometry and a different set of phonon modes in that geometry. Okay, because the way the atoms are arranged is different. Okay, we looked at those different sets of phonon modes because we can calculate all that with the quantum chemistry, and what you find is that they're different but rather similar in the sense that they really just do look like a shift in some normal mode coordinate. So the spacing of these modes is not terribly different, and the size of that's all coupled together. So the good thing is we can then we can express this set of modes in terms of these ones or vice versa rather easily, because we can just use the quantum chemistry to tell us how to shift the zero of that state. So this is carried out by adding some displacement to the creation operators and disruption operators for these phonon modes. Okay, so you only end up with one set of phonon modes in your big set of density matrices to calculate. And I won't go through that. So these are some of the vibrational modes that we can get out of the quantum chemistry. So one of these modes is a sort of oscillating mode. You can see these two are oscillating out of phase with this guy, and this is one of the modes that has quite a strong coupling to the dipole field, because you can see it's an oscillation that's taking place more or less in this direction. This kind of mode is more of a rotational mode. Okay, you can see that the sort of the benzene rings are sort of twisting like this, and this doesn't couple very strongly to the optical field, but it's still there. Okay. So actually, how you select which modes to put in your calculations and which ones to conveniently forget is actually quite complicated to choose, because you can't unfortunately put everything in. So that's the kind of setup that we have. I just want to quickly talk about two examples that we used this type of modeling to investigate. One was looking at optical amplification, where you come in with a strong pump beam, which generates lots of excitation, which then goes up to the upper state and then relaxes down and eventually gets emitted. And then you send a pulse in, which is the pulse that you're hoping to amplify, and you look at the fidelity of what comes out. In other words, do you do a good job of amplifying this pulse, or do you distort the pulse out of all recognition? And what you can see up here, you just need to really look at, you can ignore the blue and red curves. So this is the pump coming in at a particular time, 2 picoseconds. And if you time the probe beam, the beam you're trying to amplify, to come in also at 2 picoseconds, you see that you get some amplification, but and a little bit of offset in time. If you send the probe beam in later, then you develop a shoulder on the amplified probe beam, and this shoulder comes from dispersive effects, so changes in refractive index that are induced in the sample by all the excitations you have in the sample. And if you come in even later on, you don't really get hardly any amplification at all in this kind of probe beam. So there's lots of other features that you can explore with this. We've seen some line narrowing features and all kinds of features in the spectrum that I don't really have time to go through. in this kind of talk. But that's one type of application that we looked at. Another one was more of an effect of propagation, and that was to explore one of the limiting mechanisms in these types of devices, and that's amplified spontaneous emission. So if you have an optical amplifier, and at the left-hand end of that amplifier you get a spontaneous emission event, so just a relaxation of a carrier from the upper state to the lower, then that photon can then go on to cause stimulated emission as it propagates through the sample. And now you've got two photons that started off as one spontaneous event. Then your 2 becomes 4, and 4 becomes 8, and so on and so on. And so amplified spontaneous emission, if you have a high gain amplifier, can become a dominant loss mechanism. And we can simulate this amplified spontaneous emission by having a source term which is just a fluctuation in the classical light field. Okay, so you're not doing a proper quantum optical treatment of the light field, which you ought to do if you want to really model spontaneous emission. But if you trigger that spontaneous emission by a fluctuation in the classical light field, then that spontaneous emission will propagate through the sample. And what we see, if you look at the population that you can generate with a given pump field for a particular power, you can see that as you increase the power to 4 times that amount, you saturate the amount of inversion, or the amount of excitation that you can achieve in these materials. You also get lots of different relaxation type oscillations which come from the interplay between relaxation time and phase space filling effects in these materials. So that was trying to understand the kind of nonlinear pulse propagation in these types of materials. I want to talk now a little bit about understanding the interactions of these excitations between different chromophores, between different molecules. And when you make a film out of these materials, you just spin coat a film. What you end up with is all these chromophores, in a sense, more or less randomly arranged. Okay? And they're densely packed in that it's like a straw pile, really. Although there is some structure, believe it or not, all these molecules are lying in the XY plane. Doesn't look like it. But actually all these molecules are lying in the XY plane. It's just perspective that's making you think that they're not. So you have this big mess. So you have a random, to some extent, random separation between the molecules. And you have a random orientation of the molecules relative to each other. Okay? Although there may be some bias if there's a bit of a planar, if you have a spin-coated film, then they tend to lie in a plane. So what we would like to do is model how an optical excitation can move in such a pile. And in real life, you would love to do the quantum chemistry of all that whole pile, right? But you've got no chance of really calculating all that. So you have to find some way of exploring or quantifying the dipole coupling between these chromophores in a way that you have confidence with, and that you can use to map the way that an excitation will move in these materials. So there are two important processes that dominate the hopping and the way that excitations move around. One is simply that you have an excitation on one molecule, on A here, and this molecule hops to a neighboring molecule through a Forster transfer. So one way of thinking of that is that this molecule emits a photon, and the neighbor absorbs it immediately. Okay, so that's a way of taking this configuration into this one, a way of moving things around. Another important process, especially in lasers or amplifiers, is something called exciton-exciton annihilation. And in this process, you have two excitons, so two excitations, usually on neighboring molecules, but it doesn't have to be. And one of these excitations disappears, so you get a recombination, and the other one takes up all the energy and gets kicked up into a higher lying state. Okay? Again, you could think of it, if you wanted, as an emission happening from this molecule, and then this photon being absorbed by that one and kicking the excitation up to a higher lying state, which then very quickly relaxes back down to here again, okay, through some energy dissipation. And when you try to make a laser or you try to make an optical amplifier, then this process can dominate the losses, because this is effectively a loss. You're heating the sample up more or less, because all this relaxation energy just goes out into the sample, and you've got one less exciton at the end of it than you do at the beginning. So how can we quantify this dipole interaction? Well, clearly these molecules or chromophores are sort of linear. They're kind of rod-like molecules, and so what one can do is try to use a so-called line dipole approximation to quantify the interaction of two of these molecules. So this is meant to indicate one of them lying across the way and then maybe some distance behind it, this vertical one lying like this, or they may indeed be parallel with some separation, or they may be at some angle. But you can make what's called a line dipole approximation, where you break these this molecule into a number of smaller subdipoles and then calculate the dipole-dipole interaction between all the subunits. Okay? The trouble is, how do you know when you've got the right answer? So what we tried to do, or what we did was said, well, I can, in my quantum chemistry package, I can put two of these molecules in some particular configuration, and I can calculate the energy splitting I get in the quantum chemistry. And that energy splitting will be twice the coupling. Okay? So what we do is we compare the splitting we get from quantum chemistry in a particular configuration. So we do quantum chemistry of two molecules simultaneously. Okay? And then we compare that with a dipole, a line dipole type approximation, and we see if we can reproduce the quantum chemistry basically with this, I wouldn't call it trivial formula, but very simple formula. And the rationale for doing that is if we can trust this dipole formula, we can use it to model ensembles of these larger sets of molecules. Well, they can do different things, and subunits can do. They're decoupled. You mean this subunit can do something different from that? Well, but if you have a bend, then that kind of breaks the conjugation length along the molecule, so then it looks like a short molecule rather than a longer one. So it's actually then what you're looking at is the interaction of a different length of molecule. Yeah. So in it, I mean, in some ways, not in the quantum chemistry, but in this, you are thinking of it as a rod. You know, all the submolecules, all the subdipoles are parallel with each other. So this is just a set of results that really just hopefully to persuade you that we can indeed do this. And so if I take this curve, for example, this set of curves, for example, then, and this is when I have two identical molecules and I look at the angle of rotation between these two molecules. Okay? So 0 means the two molecules are parallel. They're 1 nanometer apart. And the dots, or sorry, the empty circles, are the quantum chemistry results. Okay? So if I set up these two parallel molecules, I get a splitting of the lowest energy level. I can interpret that as an interaction energy. And I can try to use that in the dipole formula to calculate what this interaction energy is, taking the dipole matrix elements from the independent molecule quantum chemistry. So you can see that we get pretty good agreement for a range of different parameters in this dipole model. It doesn't really matter what these are, to be honest. But the important thing is it's rather insensitive to the value of this number of subdipoles you have, as long as it's enough. Okay? And you can see that we also get good agreement if we try to rotate the molecule around the end. So in other words, we start again with two parallel molecules. Okay, so this number is the same as that number. And then we rotate one just around the end to make a kind of L shape, and so on and so on. So the main thing that comes out of this is that we can replace all the possible quantum chemistry calculations just by dipole calculations, as long as we're smart in the way that we break up the dipoles.
Revert back to D equals 1 when you have a light.
Why does it revert back?
P in 1 and P is 50 give you the same result.
That's right, yeah. Okay. The way that this, what P means in this model is you actually modulate the P isn't just the number of dipoles, it's to do with the number of nodes that you put into the modulation of the dipole strength. Is it going to go back that way? So each of these, for one of the sub-units, represents a piece of the dipole. And in order to get good agreement, you have to modulate that dipole distribution along the molecule and put nodes in it. Okay? And what you're actually seeing there, this is actually the number of nodes that are in the molecule, not the number of subunits. Okay? And so what this means is that essentially there's no nodes in it. And this is, super many nodes. And those two limits turn out to be the same. Okay? I haven't persuaded you. You're right in a way because there's a whole bit behind this that I haven't got time to talk about, and so it's maybe not entirely clear. I can talk to you about it afterwards. So what we can do then is now take our confidence in calculating these dipole matrix elements and use that to calculate these hopping scattering times for these Forster transfers. So this is the matrix element that we get from this dipole coupling, and we can see that we can scatter into a particular state if it's empty, and if I have something to scatter in. Similarly for outscattering, and I can model this 2-exciton annihilation where I lose one of the carriers with a similar kind of matrix element. I also have to worry about the fact that I have some spectral overlap between these scattering states, or these different molecules. So I can only make this kind of Forster hopping from this molecule to this one if the spectral lines or if there's some spectral overlap between those lines. Okay, if they're energetically very different, these two molecules, then the photon that one emits won't get absorbed by the other one. So I have to fit this kind of, or put this kind of spectral weighting functions in, but these weighting functions I can get from the linear absorption spectrum, for example. So then this gives us a whole set of rate equations for basically for an ensemble of hundreds of thousands of molecules, and then we can try to calculate some of the optical properties from that ensemble. It's worth just making the point that the spectral overlap functions are very important in that they not only tell you about the amount that you generate with a particular incoming pulse, but also the speed at which those excitations can hop around. So the more spectral overlap there is between your molecules, the faster things will move or diffuse across the sample. So this is another thing we can calculate in this model, is the diffusion length of an excitation in these materials. So what I'm going to show now is a movie of how these excitations move around, and through these spectral overlaps they localize in the lower energy parts of the sample. Okay, so I have to explain what's being plotted here. This is a small piece of the ensemble of molecules that we have, and the circles indicate the occupation, or the amount of occupation on that particular molecule. So this means that there's a high density of excitations on this molecule. This one means that there's a very small density of occupation on this molecule. The color of the dot or the circle tells you about the energy of that particular molecule. Okay, so energetically low molecules are blue. So there's a few of those around. red is kind of in the middle, and deep maroon's at the top. So what you can see if you run these simulations is that firstly you generate lots of excitation. That's your pulse coming in, and then as time rolls on, the excitations tend to localize into the lower energy regions of the sample. Essentially, it's like water flowing downhill, but this all emerges out of the spectral overlaps of these functions. But not only that, because it's just looping again, so it doesn't jump back up again. Because you localize in these low energy regions, then that also stimulates this exciton annihilation to happen, because locally you pull things into regions of high density. Okay, so that increases the losses as well, because they find each other and then they annihilate. So that's the kind of simulation that you can do for these particular types of materials. How does this relate to an experiment? Well, our collaborators at St Andrews University have done measurements of a quantity called the anisotropy in these types of films, and made up of exactly these kind of materials. And I should just say what that measurement is. They go in and they excite the sample with a linearly polarized light beam, and then they look at the polarization, and now I mean the polarization as in X or Y or circularly polarized. They look at the polarization of the luminescence that comes out. Okay, and what that tells them is how is the dipole that they generate with their light field, how is that related to the dipole that emitted the light that they measured? Okay, and so if the excitation is hopping from one of these molecules to another, then it will be exciting a dipole that's lying along a differently oriented molecule, and so the emitted light won't anymore be in the same direction as they generated it. Okay, so this is a measure of how fast these excitations move around, hop around in these samples. So if you have a perfect rod-like molecule, then the initial anisotropy that you expect is this value of 0.4. Okay, you might think it should be 1 in the beginning, but it's not 1 because with your incoming light field, some of the molecules are lying like this, and so you don't excite them as efficiently as you would excite something that's like this. Okay, so they're not perpendicular to the momentum of the light. So you start at 0.4, and what we see here is within 1 picosecond or so, we've started all this hopping mechanism across all these different molecules. And what you see in the circles are the experiments, and the lines are simulations that we've done at different emission wavelengths, and you can see that they all pretty well agree with the experiments. I should say that we really, apart from fitting the spectral overlaps of the emission and absorption of the materials to give us some line widths, we haven't really fitted anything to get this agreement. So this timescale comes out of the quantum chemistry simulations and the dipoles that produces. And so we're pretty happy to get this kind of agreement. So my time is basically up, so I'll skip those last 3 slides unless anyone wants to kindly ask me about them. And I, of course, have to acknowledge my collaborators, Jean-Christophe Denis, who's one of my PhD students, Martin Patterson, who's a colleague in chemistry, Stefan Schumacher, who did much of this work, who used to be a postdoc here. Some of you will maybe know him. The experiments were done by this team under Ifor Samuel at St Andrews, and the clever chemists I mentioned are Peter Skabara and Alex Kaniblowski at Strathclyde. So with that, I'll finish. Thank you very much for your attention.